why I do this, guys, the reason why I do that timetable with you and to put the pressure like that is because if you fall back to the old school method of how to factor, how you utilize terms, it makes your life easier as opposed to a lot of the newer methods of the boxes and all that other stuff. There's nothing wrong with any of it. I'm not going to tell you one way is better than another, but I'm going to use the same method over and over and over and over again. Okay? And here's what I do. You guys can put that stuff away. You can keep it if you like. I know you guys all want to finish it. So go ahead and get your stuff back out. Like I was saying, this is very similar to what I had you guys look at as far as that goes. As we get into factoring, remember, we're taking a quadratic equation or a quadratic statement in this case, there's no equal sign. And we're going to write it as a product of two terms. Remember, when I say the word terms, you're going to see me put parentheses up a lot because terms create zeros. Inverse of zeros create terms. There's a lot of things that go back and forth there. What happens with the quadratic formula, or not quadratic, excuse me, factoring, I use the old school method of what do you multiply to get your value of C that adds to get your value of B. Okay? I use that T-chart method. What times what's negative 28? You add together to get negative 12. Remember, if you're multiplying two things together that are negative, that means you'll have one negative and one positive. Now, if the middle term is negative, that means the larger of the two multiples has to be negative. Yeah, it has to be negative. And it's one of those things you can check off real quick. So you start thinking about, all right, my factors of 28, 1, 28, 2, 14, 4, 7, and that's about it. Which of the combinations give you those? 14 and 2, yeah. So you get x minus 14, x plus 2. Does it matter which one of those terms comes first? Nope, because you're multiplying. Does the order matter in multiplying? What property is that? Good. No, the no order matter property? Very good. All right. So, do you remember how you could check to see if you got this correctly? Foil it. You can foil it back out. Remember how to foil? Yes, first you go first, outside, inside, last, otherwise known as Billy binomial. What? Oh my God. How do you guys not know Billy binomial? All right, let's try another one. I'm surprised you guys never saw Billy binomial. X squared plus 4x minus 21. What times what is negative 21? You add together to get positive 4. Positive 7, negative 3. This is the idea of understanding and knowing your factors quickly. If you know your and that's why I do that times table thing. If you remember your factors quickly, it just makes the math easier. You're not spending time wasting your time trying to go through the list of things. You're not trying to sit there and put everything through on the calculator because it's a waste of time. You get x plus 7, x minus 3. Okay? Maybe you remember this, right?
Yes.
Okay.
I remember.
Careful. Actually, I should say the first rule of factoring is to look for a what? GCF. GCF. In this case, there is a GCF. It's what? 2. So if you factor out the 2, you're left with that. What times what's negative 12? You have to get 1. Very good. Negative 4 and 3. What changes when there's an equal sign versus just factoring? What do you have to look for? Remember what it's called? When you have factored forms and you have an equal sign, what that means is it's asking you to find the zeros. You're solving for x. You set both of your terms equal to 0. Basically, this right here is intercept form. That's intercept form, like we talked about yesterday for graphing, which means your zeros will be located at the zeros of the terms. That means you set them up. So you have zeros at 4 and negative 3. That would be the solution to these types of problems. Whenever you see an equal, after you factor, you set your terms equal to 0. Okay. Basically, this is setting us up for, and I was talking to 12th hour about this yesterday, this is setting us up for what's going to be called eventually the fundamental theorem of algebra. What that states is that whatever nth degree polynomial that you have, nth degree just means whatever the degree is. In this case, the second degree polynomial because it's a square. Okay? For any nth degree polynomial, there exists exactly up to n zeros, n possible zeros. So this means with a second degree polynomial, you can have up to 2 zeros. Cross the x-axis, up to, and then you get 56 zeros. We can build polynomials. If we know what the zeros are, we can build polynomials. We can go back and forth with all these things. Okay? Knowing that you have, well, for example, if I know that I have zeros at negative 2, bless you, and 5, or excuse me, 3. If I have zeros at negative 2 and positive 3, what are my terms if those are my zeros? If my 0 is negative 2, what's my term again? Yeah, it'd be x plus 2, and this would be x minus 3, and I could build the polynomial and get x squared minus x minus 6. That's not today, but that's something we will eventually be able to get to because we'll have to know a little bit more information if A was positive and things like that. But the idea is that you can build polynomials if you know your zeros. Okay. We'll get there. There's also these crazy things with some special patterns. For example, that's called difference of squares. The reason why it's called difference of squares is because what's that symbol in the middle? Subtraction. It's a minus sign. So whenever you see two parts to a quadratic problem, is the first term a perfect square?
Yes.
Is the last term a perfect square? You guys remember what perfect squares meant?
Yeah, it's like on the 17.
Yeah, 4, 9, 16, so on and so on and so on. So what that means is that if these are both perfect squares, and that's a subtraction symbol, you get x plus 3, x minus 3. Okay. What changes here? What's the square root of 1? 1. So that means you factor like you would normally and then look for its zeros. So whenever you see an equal sign, you factor like you would normally, and then you take that one last step to find the zeros. If you don't see an equal sign, you're going to stop at factor 4. It's failed. So this means that when you factor this out, those are your answers. Can you write it like that? Plus minus 1, can you have the answer like that? Sure, absolutely. I'm all for saving ink. Yeah, I do. Okay. What do you factor that to be?
Wait, how do you know?
All right, hold on. Remember, this is the exact same thing as this. I put a 0 in for B. So this is asking you what times what is positive 16, but it adds together to get negative, or excuse me, adds together to get 0. Nothing. This is not a factor. That's not factor. What's that? What's that? There will be a solution to that here in about a week.
Why'd you look?
Have the date on here.
Wait, if it's not factorable now, but then there's a solution to it later, then is it not factorable or is it factorable?
Right now, it's not factorable. It's
Then why
not
teach us?
because for right now, there is no way to do that. You have to learn how to do other stuff prior to learning something else. I need to build your schema. I'm just making up words. X squared minus 6x plus 9. Positive 3s or negative 3s? Negative 3s. Very good, very good. This is what you guys call junk times junk. Right. Junk times junk is the exact same thing as writing it as junk squared. Now, for those of you guys that had Seth, this was a giant pet peeve of his. Because if you had to FOIL that out, what would happen? You guys would kill puppies. Remember, this does not equal x squared plus 9. This is when puppies die. But guys, remember, if you do that, a puppy. So don't do that. But yes, when it gets down to this, can you write it as term times term, or can you write it as term squared? Does it matter? To factor it out, it's okay. It works either way. It's fine. There are rules for some of the special patterns like that, but I find that it's much easier just to kind of write it out without doing the special patterns. We'll get to special patterns when we have cubics and things like that later. Okay? Take a minute. Get your zeros, please. All right, what times what's negative 30? You add together to get positive 1. Where are your zeros then located? 5? 5 and negative 6. All right. What? Yeah, sorry. What times what's 9? You add together to get 10. 9. Very good. Zeros then are located at? Now, I know that a lot of this is review to start off with. I do want to kind of briefly kind of lead into some of the stuff that you do when you have coefficient first term that is not equal to 1. Because in essence, you are doing the exact same thing. For a quick example, x squared plus 10x plus 9. What we did there is we figured out what times what is 9 to add together to get 10. We knew it was 1 times 9. Okay? That's what we did. What's the coefficient of the x squared? What's the value of a in that quadratic statement? It's 1. So really, what I did is I multiplied, you'll hear me say this, I multiplied my tails to get the middle. My tails would be the 1 and 9. It just so happens that we don't say that because the coefficient is automatically 1. So when we switch over to doing stuff that has a leading term coefficient that is not equal to 1, for example, 3x squared minus 17 plus 10. But when you do is you still follow the exact same process. And again, I know that there are so many different methods for factoring when your leading term is not equal to 1. I fall back to the same method over and over again. I like to use the method called factor by grouping. Okay? What that is that I'm still going to multiply my tails together. I'm going to take the 3 times 10. Very good. What times what is positive 30 that adds together to get negative 17? That tells you that they both have to be negative. Okay? The middle term's negative, the last one's positive. Both terms have to be negative. So what would that be? Negative 15, negative 2. Very good. Now, I call it factor by grouping. It's also sometimes referred to as split middle term. Remember that? Because what I'm going to do here is I'm going to split this middle term into, well, 3x squared minus 15x minus 2x plus 10. Okay? How many terms do I have now in my statement? 4. Whenever I have 4 parts to an algebraic statement, whether it's any polynomial, I'm always going to try to factor via grouping. What that means is I'm going to throw parentheses around the front two and take the GCF. Okay? What's the GCF of 3x squared and 15x? 3x, very good. What am I left with inside then? Good, x minus 5. Okay. So now, what I need to do for the second set is that I'm going to try to get the term in parentheses to look exactly like the x minus 5. But here's the trick. Notice how I have both, when I split that middle term out, both of them were negative. One quick reminder that I will tell you guys is that I always do a same change opposite, because that way it reminds me that I need to factor out the negatives. So I'm going to bring out negative 2, and what's 10 divided by negative 2? Okay. That is just a little way that I've always done it to help remind me that I got to factor out that negative. And that's how the signs change. So now it becomes the easy part. Are the two things that are written in the parentheses the same? Write it down. What's left? And then you're done. Okay? Because basically what you've done there is that you've done GCFs a couple of times. Really, you've done 3 GCFs. You did a GCF for the 3x minus 15x, you did a GCF for the negative 2x plus 10, And then with this term here, they both share the x minus 5, and you pull that out. So basically, it's 3 GCFs. Yes, ma'am. Yeah, it works. It works. It just, with ones that are not coefficients of 1, I'm sorry, when they have coefficients of 1, this just takes longer. I mean, I have no problem with it. It's fine. And that's why I always say I don't care how you do it. I'm going to use the same method for either one of them because I think these are more efficient. But I'm not going to say no. All right. All right.
Does that vaguely ring a bell?
It usually takes a minute or two. We usually take a day and a half to get through these things just to get our brains back on how all this stuff works. It's not a big deal. Welcome. It actually works out real clean real fast, doesn't it? What times what is 144 that you add together to get 24? 12 and 12. So this splits out to be a 9x squared plus. Oh yeah, by the way, I'm just gonna say that. Hold on. The textbook, all textbooks for some godforsaken reason change the variables all the flipping time. It drives me up the wall. There's no reason to. Just use X. Anyway, yes, I changed them to X's. Hey, look, everybody! I changed the Y to an X. It's magic. Thank you, thank you. I am nothing but the greatest man alive. What's the GCF? What's the GCF? 4. Are the things in the parentheses the same? Yes. Write it down. And what's left? This is another one of those jump squared problems. It is a quantity 3x plus 4 quantity squared. Do you have to write it like that? Nope. You like that. Okay. Let me give you a handful of factor ones out of 5.2 to work on. So I forgot what page that is, and I'll make sure to give the 12th hour the exact same problems this time around. They're all about the same. I'm going to put it on the calendar right now. Hold on. Just so you guys know, these are half of them coefficient 1, half of them coefficient not 1. You don't have to find zeros for any of these. Okay? These are just straight factors. We'll do more zero stuff tomorrow. Yes, sir. Up shelf, man.